Welcome to the Worldwide Center of Math's basic series for complex analysis. For this video, we're going to talk a little bit about Cauchy's integral formula. So this formula says it's a neat little formula that says f of z is analytical in some domain. We have a contour integral closed loop whose interior and the loop is contained within this domain. The integral of f of z over z minus z naught dz is 2 pi I f value of f at z naught. So we can show that this is true. First, let's So first thing, we can establish that this integral, in fact, equals 2 pi I. To do this, we can plug in, and we're integrating over a circle centered at z naught of some arbitrary radius. So plugging in z equals z naught plus r ei theta to parameterize our curve in terms of theta. We'll see this simplifies to z minus z naught, just r ei theta. dz is r I ei theta d theta. This whole thing just becomes integral of 0 to 2 pi I d theta, which is just 2 pi I. So that's a quick showing that this integral is in fact 2 pi I over any circle centered at z naught. So now we're going to consider this this difference, the magnitude of this difference, the integral f of z over z minus z naught dz minus 2 pi I f of z naught. Now we established 2 pi I is in fact just the integral of 1 over z minus z naught over some circle. So plugging that in, we can rewrite this as f of z naught over z minus z naught dz. We want to take the integral, and the integral of that thing. And we're assuming also, remember, f of z is analytical in our domain here. So writing again, considering that z minus z naught is r ei theta, f of z minus f of z naught can become as small as we want, as small as we want as we shrink our circle. And also note that we can approximate this it's less than or equal to the max of the modulus of the thing inside times the length of our contour integral. And this is easily established by looking at the sum using the triangle inequality. We get something like this. This is a useful estimate or bound for an integral. So now on our circle, z minus z naught is really just the radius of the circle. It's constant. Now we're assuming f of z is analytical, so it's continuous. F of z minus f of z naught, we can say it's going to be less than epsilon over 2 pi for a small enough circle. And then the circumference of the circle is just 2 pi r. So putting all this together with our estimate, we have epsilon over 2 pi r times 2 pi r is greater than this, which is just equal to epsilon. So this thing, as we shrink our circle, can become arbitrarily close to 0. So this thing can go as close as we want to 0. So one last thing we can note before confirming Cauchy's integral theorem is that the integral over any of our contours, including these circles, will all be in fact equal to each other. So we can establish this if we assume Cauchy's integral theorem, saying that the integral where a function is analytical, it's analytical on a domain. We have a curve in the domain whose interior is in the domain. The integral is just going to equal 0. And so So we can consider we have a point. Our function f of z over z minus z naught is analytical in the domain not including z naught, and also where f of z is analytical. So saying this area is all going to be analytical, this area is all going to be analytical. So if we integrate this part here and this part here, both of these integrals are going to be 0. If we add them together, these two parts cancel out, and we'll get that the integral of this part contained in this part are both equal to each other. And so we take any two arbitrary curves, they'll both be equal to some curve they contain. So any contour integral in these regions will all be equal to each other. So from this, we can conclude that as we shrink our circles, all these integrals are going to just constantly be equal to each other. And so none of these integrals can be greater than 0, because as we shrink our circle, they approach 0. And so this thing must equal 0, and so we have and so we can conclude Cauchy's integral formula. And that establishes that. Thanks for watching. If you like this video, please check out our other complex analysis videos. Thank you.